Hello, my name is Samuel Mercandal and I work at MIT Lincoln Laboratory. Today, I will present our work titled Cross-Language Attacks, in which we present a new attack methodology to circumvent commonly deployed defense mechanisms. Our work investigates the new paradigm of multi-language applications, or MLAs. These are applications that deploy multiple different programming languages in one application. Unfortunately, we show that because these different languages may choose to deploy different defenses, inconsistent threat models between languages may lead to new attacks. In particular, we introduce cross-language attacks that take advantage of these inconsistencies. For example, below, we see an MLA that consists of Rust and C, where Rust deploys memory protection and C deploys control flow integrity. As the program executes, control flow may transfer from Rust to C, in which there may exist a bug in the C code that can lead to memory corruption. This memory corruption may then be leveraged by an attacker to corrupt an indirect jump that will be later taken in Rust, where there is no control flow integrity deployed. This attack was really possible because of an inconsistency between these languages. Namely, C deploys control flow protection, but not memory safety, and Rust deploys memory safety, but not control flow protection. In order to look at the origin of these different defenses, we can see that throughout the last few decades, there have been many influential defense mechanisms suggested, but they're always followed by other advancements in attacks. This eternal war has created a tension that has led to little change in observed CVEs. For example, the graphic in the middle shows that between 2006 and 2018, memory safety consistently caused around 70% of all CVEs at Microsoft. Moreover, these statistics also have been reported by other companies such as Google. Alternatively, some believe that new safe programming languages will be a catalyst for real change in this eternal war because they show promise to be able to prevent memory problems at the onset without insane performance costs. Two examples of new safe programming languages are Rust and Go. These both have strong type systems that can facilitate many of the needed compile time security checks, such as preventing arbitrary casting, but they also include proper runtime checks for dynamic data. Both languages also provide temporal safety, just with different strategies. Namely, Go leverages garbage collection and Rust uses lifetimes and ownership. While these runtimes are not identical, the main point is that these languages both support security with runtimes acceptable even in the systems domain. Unfortunately, there are 50+ years of legacy code that cannot be immediately rewritten. Thus, these new languages must offer strong and flexible foreign function interfaces, or FFI, that allow interoperability between languages. This facilitates the incremental deployment of safe languages into code bases, which is what we refer to as multi-language applications, or MLA. In fact, we see that this trend is common in industry with many applications such as Firefox or CockroachDB. While we fundamentally support the incremental deployment of safe languages, our work does demonstrate that if not done carefully, this incremental deployment can actually reduce security. In particular, as you will see today, we create a graphical model to represent the new threat model of multi-language applications and show that many variants of our cross-language attacks are possible in this new setting. Of course, we cannot discuss everything in this presentation today, so we encourage the listener to seek further details in the paper. In order to set the stage of our attacks, we first highlight some details of Rust safety guarantees. The main driver of Rust safety is that it forces mutation XOR aliasing. A program is allowed to mutate or alias memory, but not both. The two pillars of Rust that drive this idea are ownership and lifetimes. You can pass by value to a function to transfer ownership, or you can pass by reference to temporarily borrow ownership. This borrow can be mutable or shared, where the mutable borrow allows mutation but not aliasing, and a shared borrow allows aliasing but no mutation. The temporary nature of a borrow is described through lifetimes. After the lifetime of a variable ends, Rust can perform automatic memory management to free the variable. Additionally, Rust leverages what is commonly referred to as fat pointers that associate metadata with data to prevent spatial errors, as seen below with the vector type, or vec. In fact, on the right, we can see a simple Rust program that creates a vec, borrows the data to other functions through both mutable and shared references, and finally transfers the ownership to another function. After the ownership transfer, Rust can no longer borrow or use the data. For example, line 18 would cause a compiler error in the program. We also see the discussed spatial and temporal safety guarantees by Rust in this example. Lastly, in order to be usable in the systems domain, Rust must allow an escape hatch from its strict type system for performance optimizations or other low-level device management. For our work, it's important to note that while Rust does force the use of unsafe or FFI calls, FFI only describes the intended interactions between languages. One line of unsafe through FFI opens the door to many other unintended interactions in which the language can influence the other language, for example, through their shared address space. In order to get an understanding of how this relates to multi-language applications, we first observe the threat model of a C program with no defenses. An attacker will start execution, try to corrupt memory, inject gadgets, hijack control flow, and eventually execute a weird machine. One approach to prevent this flow is to harden C with a defense like control flow integrity or CFI. This defense removes the control flow hijack block to limit both the attacker's path, but as we have seen in the recent literature, this cannot prevent other more advanced data-only attacks. On the other hand, a safe language removes the memory corruption node altogether and prevents all paths for the attacker. Unfortunately, when we combine these approaches, as is the case for MLAs, we actually end up where we started, when there was no defense applied at all. An application can start in C and use the new language transfer node in the attacker's path to move into the safe language that has no control flow hijack protection. Therefore, we see that adding something good, a new safe programming language, to something that has historically struggled, like C hardening techniques, may actually leave us with something worse. Next, we extend our threat model into a descriptive graphical model that can represent many forms of our cross-language attack. As one can see, this model contains the same basic blocks as the previous page, but with additional details. For example, with our model, we can overlay particular defenses on either language, such as CFI and the shadow stack for C++, and lifetimes, the borrow checker, and dynamic bounds checks for Rust. Additionally, our model is indeed hierarchical, and in that we can zoom in more detail for each node to more concretely describe languages and their defenses. Moreover, our model is expressive enough to overlay specific attacks, such as the attack presented in a recent TOPS paper that follows our motivating example from earlier. This facilitates a clear visualization as to how an attacker can bypass any deployed defenses. However, a critical advantage of our expressive model is that we might be able to use it to identify other cross-language attack variants. One such variant we describe in the paper is how to corrupt Rust spatial safety guarantees. Here we show a simplified code example where Rust creates a vec and calls a C function that contains an out-of-bounds error at line 8. Thus, we can use the memory corruption in C to overwrite the fat pointer associated with the Rust vec. This leads to cascading spatial corruptions as the dynamic chests in safe Rust will now fail to identify the out-of-bounds access, for example, on line 8. Similarly, we can corrupt the temporal safety guarantees of Rust. In particular, we show an example where a C function mistakenly frees a pointer associated with Rust data, which will cause incorrect lifetime calculations in Rust. This will lead to the use after freeze seen on line 6, as well as a double free after the Rust function completes. Given these cross-language attacks, we want to identify how frequently their primitives appear in real-world MLAs. In particular, we have two main research questions. First, we want to see how often language transitions actually occur. And second, we want to understand if language transitions are widespread toward a diverse set of functions or limited toward a select set of functions. We perform this evaluation on the Mozilla Firefox codebase as it is an example of a large open source MLA. To answer our research questions, we define a set of metrics related to language transitions. First, we define call sites for a function as when that function is the caller of another function. As a subset of call sites, we are interested in transfer points or call sites that are a function call to another language, and indirect and dynamic calls that are building blocks for our CLA variants. Similarly, we are interested in the behavior of invocations where a function is the callee of another function. In particular, we want to investigate visitor points or invocations that cross the language boundary. Finally, we will end our evaluation with a discussion of the distribution of language transitions across functions and identify any heavy headers in this distribution. For our call side analysis, we present the following table where each cell contains the raw magnitude that we collected, as well as the column percentage and row percentage of its subclass. For example, we found 12,000 transfer points in Rust functions, which is just over 3% of all call sites in Rust, and over 5% of all transfer points in the entire binary. While these percentages are small, we note that the actual magnitude is quite large. Moreover, we see that many of the needed building blocks for CLA and Rust functions, and that over 50% of all call sites in Rust are indirect calls, and over 38% of all call sites are dynamic calls. In fact, this behavior is unique to Rust when compared to C and C++ code. For our invocation analysis, we see that the majority of Rust functions come from memory unsafe languages, and additionally, most language transitions go from C, C++ toward Rust. From this, we can conclude that Rust mostly acts as a service module for C, C++, which is notably in line with the idea of multi-language applications. Finally, for our heavy hitters analysis, we see that while most transfers are toward Rust, when Rust calls a C, C++ function, it is most commonly associated with libc. This makes sense as the Rust standard library is built on top of libc. In particular, we posit that this is a fruitful area for future defensive work against CLA to focus. In summary, we investigated the new paradigm of multi-language applications where we presented a graphical threat model and demonstrated that different languages have incompatible assumptions. In particular, these inconsistencies may lead to many variants of our cross-language attacks, where an attacker maneuvers between languages to circumvent deployed defenses. Lastly, we demonstrated that the existence of many building blocks of CLA in a real-world multi-language application. We distribute all of our code as open source, which includes our evaluation as well as a number of more complex proof of concept code examples. Thank you.